Hello, my name is Dr. Molly Domino. I'm an assistant professor here at Corey College up in the Roo. I've currently been teaching our CS 5001 course, which is part of the Align program, and is a great course if you have no CS background and need a crash course on the basics before getting into the master's program. It's my favorite course to teach, and I'm really excited to share with you a little bit about what we do in that course. So I want to talk to you about a question. Why do computers think in binary? Which you might think has a really succinct answer, and this is a 2-slide PowerPoint and we can all go home, but it's actually got a lot of side history we need to discuss to give the full context of why it is that this is the way that it is, and we think about computers think in this 0 and 1 way. In counting systems that we use in a lot of the West, we use a base 10 system, so we have unique symbols for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we start combining symbols together to make larger numbers. So 10 is really a 1 and a 0 together. Binary is the same thing, except we just use 1 and 0, and then we start combining those two together to make larger numbers. So 2 ends up being 1, 0, 3 is 1, 1, and 4 gets up to 1, 0, 0. So before we get into computers and their counting systems, I think it's worth backing up and actually pausing to question why we use the number 10 as our cutoff point. Why do we have unique symbols for 0 through 9 and not 10? And it ends up being that most cultures in the modern day, only a very, very few don't use a base 10 system for their counting systems. In Arabic numerals, you would see 9 groups of 10 and 1 extra as 91. Ancient Mayan had a system which was a base 20, so we had 4 groups of 20, or those 4 dots up top, and then 11 more are the 2 lines and the dot at the bottom. Ancient Sumerian was a little bit unique. They used a base 60 system, so we had this one symbol on the left is 1 group of 60, and then 11 more. All 3 of these represent 91 in different combinations of symbols. But most today use a base 10, and the reason for that actually has to do with my hands, right? We have a very convenient counting system. If we think about prehistory, before any systems of writing were invented, we had a really convenient way to count. 1, 2, 3, 4, 5, right? Mayans used fingers and toes. That's why they used a base 20 system. Ancient Sumerians used a system of counting knuckles. So that's how they got to 60. Everybody ends up using hands and other body parts as an initial system of counting throughout history. So let's move a little bit more forward in history, because that's our baseline. Now we have some system of writing. I have a stone tablet and a way to dig into that stone tablet. So now I can make some amount of marks, but they're going to look like tally marks. They're going to just look like a straight line in a piece of stone, because that's what's convenient to a busy merchant on the go who just needs to mark how many apples they've sold that day. Now we'll fast forward a little further. Writing systems get a little more complex. I, as a very busy merchant, start selling thousands of apples. Ticking in 10,000 tally marks a day is not what I want to be spending my time with, so we start inventing more robust systems for symbolizing large numbers. So ultimately, the history of counting starts with what was most convenient, and we end up creating a system of symbols that uses what's most convenient for humans. So we could say that a very easy answer to why do computers think in binary is that it's the most convenient for computers. But if I ended the lecture there, it's not really answering the question, is it? We don't really know why zeros and ones are most convenient. To answer that, we actually have to go on a completely different sidebar, and we have to talk about fabric. So again, we're going to go back to early history. Fabric was, especially intricate fabric, was first created using manual looms, using your hands and the pieces of string, and maybe a couple things to keep everything organized. Weaving fabric is not my area, but I do know it was a pretty slow system and pretty tedious to keep track of every single thread on a particularly complex piece of fabric. In the early 1800s, we see the invention of the jacquard loom. And this is a mechanical loom that allows us to create pieces of fabric that is controlled by a machine that uses punch cards. These pieces of paper with holes punched into them. Essentially, there was an array of needles, each one carrying a color of thread up top. You would slot in one punch card, the array of needles would come down. If they fit through the hole, then you would see that particular color of string in the fabric at that particular line of weaving. If there was no hole, then the needle would just stay on top and you wouldn't see that color. So it was a way of controlling which colors you saw at which particular point in your fabric. And it allowed for much more complex designs, or equally complex designs with a little bit easier overhead in terms of time and manual labor. Then we move about 40 years into the future, in the 1850s area. We see George Boole invents a system of algebra called Boolean algebra, named after him. Don't worry, I'm not going to make you count today. Boolean algebra is actually something I learned a lot more about in my philosophy classes than I did in my computer science classes. It's a variant of what Aristotle called propositional logic, if that rings a bell for you. It really only worries about the ideas of true and false, yes or no. I'm going to go eat pizza today, or I'm not. So that brings us to the kind of combination of this mathematical invention and this mechanical invention. We see two people work together to start creating what's called the Jacquard loom for math. These two names might sound a little more familiar to you. You might know of Charles Babbage. He invented what's called the analytical engine, which is a calculating machine that is controlled by punch cards. It essentially, when he first created it, just created a mathematical series of numbers. So each one takes the previous numbers, does some math to it, and then you get another number in our sequence. He showed it off actually in a lecture, which was written down in Italian and read by Ada Lovelace. She then transcribed that from Italian into English and about tripled the length in notes, because where Charles Babbage initially saw this as a calculating machine, she saw the idea of using Boolean logic and making this an anything machine. Those two worked together over letters and in meetings in terms of correspondence to more fully flesh out the idea of what was called the proposed difference engine. And that was a machine that would use punch cards to help control the calculations that it could run at any given moment. These might start looking kind of familiar to you. Maybe you've even heard of a computer that uses punch cards before. But I want to stop and note the important part of what a punch card is, right? We have only two possibilities. There either is a hole or there isn't one. We don't really ever have a situation where there's half of a hole. Doesn't even make sense. And that ends up being pretty similar to a lot of the other things we've talked about today. In terms of Boolean algebra, there's only two possible states. You're either true or false. I'm either yes eating pizza or I'm not. Or a 0 or a 1. All of these concepts really end up transferring very well to each other. A 0 could represent no hole. A 1 could represent hole. True could represent yes, there's a hole here, or false isn't a hole. They all are kind of analogous, is my point. So then I need to gloss over a little bit more history, and we move ahead to 1945, so about 100 years later. And we get to the first general purpose computer, which is called the ENIAC computer. And it is still controlled through punch cards. All computers, since their real genesis in the 1850s, have been using this Boolean logic, this punch card approach, to their computations. Which is another half answer to the original question, right? Computers think in zeros and ones because of Boolean algebra, and they've always kind of been like that. But that's not always a great answer either still. We've had a whole century at this point. We didn't think of anything better. It's 2025. We didn't think of any other options besides this. And ultimately, we don't use punch cards in our computers today. But we still end up using Boolean algebra, the idea of a 0 or a 1. So I want to pause again, last sidebar here, and talk about what Boolean algebra really is. It's mostly what I've said already. If it is Tuesday and it is 6 p.m., then I'm going to go to trivia. In a circuit representation, it might look like this. If there is electricity in our left two prongs, then we're going to put electricity in the right side prong. Otherwise, if one of these is off, then our right side prong does not get any energy to it. And it's this idea of electricity or no electricity in a particular transistor that binary ends up translating really effectively to. We can either see, yes, a transistor is on, like a light switch, or it's not. We don't have to worry about how on a transistor is, how much energy is being pushed into that particular piece of wire at a particular moment. If we had a system of 0 to 9, we'd have to think, all right, is this a 5 or is this a 6? And differentiating between those things ends up being a pretty complex and strenuous task for a computer. So much harder, especially than, is there electricity here, yes or no? So the ultimate answer is that computers think in binary because transistors work really effectively with binary in terms of, is there electricity here, yes or no? And we've had a long storied history of understanding computers using binary logic, so it's very easy to keep going and continuing with that history. That's the quick and dirty overview. This is an extremely deep rabbit hole that I myself kind of went down because it was an enjoyable rabbit hole to explore. I really encourage you, if you're watching this, to go do a little bit more research into this. I am not able to talk about how wild all of these people's lives were. Everybody that I've mentioned, George Boole, Ada Lovelace, they've got extremely interesting life stories, and I hope you get to explore those and see how they all work together. If this has been interesting to you, I would like just to note that the Boolean algebra and this idea of and is one of 3 major components. There's an and, which I showed on screen, an or, which is pretty similar, it's just either or of 2 options, and not, which is just saying that it's not Monday. If you can master these 3 components, mathematically you can solve any algorithm. You can represent any algorithm as a series of ands, ors, and nots. So if you're interested in computer science and you can grasp those 3 ideas, then you're off to the races. I've done 90% of the work. Thank you so much for listening. I hope this has been enjoyable to watch.